Hello everyone. In the lecture number 27 of the lecture series of thermodynamics, the topic is very interesting. It is Carnot cycle in the temperature entropy diagram and also in the ST diagram and VP diagram also. Suppose it has already been discussed in the PV diagram, when P in the y-axis, V in the x-axis. But what about if their order is reversed? That means V in the y-axis and P in the x-axis. Similarly, the temperature entropy or entropy temperature. Okay, all this would be discussed in this lecture. So in the TS diagram we have to make an equation, and since this is a cyclic process, so the first law of thermodynamics, the cyclic integration can be done with this also, for the Carnot cycle being a cyclic process. Okay, and we find that cyclic integration of du is equal to 0 because this is a state function. U is a state function, and conversely cyclic integration of TdS minus cyclic integration of PdV would also be equal to 0. That means cyclic integration of PdV is equal to cyclic integration of TdS. So here all the integrations of PdV would be substituted by integration of TdS. Okay, so let's see Carnot cycle in the TS diagram. Okay, so here is the diagram. You see the A to B, this change is isothermal reversible expansion. So isothermal reversible expansion means temperature is constant. So since temperature in the y-axis, so it should be parallel to the x-axis because there should be no change along the y-axis. But as I have said during the numerical problems, that entropy increases with increase in volume. V is increasing. Okay, so if volume is increasing, entropy increases. So here it is expansion, so entropy must increase. So entropy increases from S1 to S2, but the temperature remains the same, T1 to T1. Okay, it remains the same. Next is adiabatic reversible expansion, that is B to C. So since it is adiabatic, no heat exchange is taking place. As a result, the temperature is dropping. But since there is no heat change, dq is 0, so dq by T is also 0. That means ds is 0. ds is 0 means entropy remains the same here. That means entropy changes from S2 to S2. That means no change. It remains S2 throughout. But temperature drops from T1 to T2. So it is parallel to the y-axis and it is perpendicular to the x-axis. Okay, so this way we are getting a rectangle. Now the reversed directions, this is isothermal compression and this is adiabatic compression. Okay, so isothermal compression from along the x-axis from right to left, and adiabatic compression along the y-axis from bottom to top to the initial position A. So temperature here remains the same, temperature drops, then remains the same, then increases. Entropy here increases due to expansion, then remains the same due to no heat exchange, decreases due to compression, now remains the same due to no heat exchange. So this is the TS diagram of Carnot cycle. Now what about the work calculation? As we find that W expression, which is actually PdV, okay, here instead of doing integration of PdV we have to do integration of TdS, because PdV, cyclic integration of PdV is equal to cyclic integration of TdS, and the integration limit should be S1 to S2. So the result is for W1 it is T1 into S2 minus S1, and this is nothing but equal to the heat released by the system Q. Okay, now B to C, this is adiabatic. So here it has its own expression, adiabatic change, Cb T1 minus T2. This is same as the PV diagram. But CD, C to D is isothermal reversible compression. So the entropy changes from S2 to S1. So the lower limit is S2 here, but the upper limit is S1. And the temperature is T2. It is taking place at T2 temperature. So it is T2 ds. And the result is T2 into S1 minus S2. So if it is multiplied by minus 1, then it becomes minus T2 into S2 minus S1. Okay, multiplied by minus 1, outside the bracket, inside the bracket. Outside bracket becomes minus T2 and inside bracket becomes S2 minus S1. And this is nothing but equal to the amount of heat released to the surrounding or the sink. So this is minus Q prime. Okay. And finally, the adiabatic reversible compression dA would have the same expression Cv into T2 minus T1. Okay. So these two are just opposite to each other, W2 and W4. So these two would be cancelled when summed up, all these 4 W terms, only remaining this one, Q minus Q prime. That means T1 S2 minus S1 plus minus T2 S2 minus S1. That means minus T2 into S2 minus S1. So here, if S2 minus S1 is taken as common, then we get T1 minus T2. So it is S2 minus S1 equals to T1 into T1 minus T2. That means S2 minus S1 means this one minus this one. That means DC. Okay. Into T1 minus T2. That means this one minus this one. That means BC. So DC into BC is the area of the rectangle. So area of the rectangle ABCD is the work produced by the machine, Carnot engine. Okay. So this is the TS diagram. Therefore, efficiency is minus W, work produced by heat supplied Q. Okay. And we have got the value of work produced, S2 minus S1 into T1 minus T2. And Q, what is the value of Q? Q has the value, this one. This one is the value Q. Q is T1 into S2 minus S1. So we put the value here, T1 into S2 minus S1. So S2 minus S1 would be cancelled. And then what is left? T1 minus T2 by T1. Okay. On the other hand, W can also be written in terms of Q and Q prime, like W1 Q and W3 minus Q prime. On the other hand, W2 and W4 the same, just having the same magnitude with opposite signs. So W2, W4 would be cancelled by each other, while it remains Q minus Q prime. Okay. So instead of minus W modulus, we can replace here this value here by Q minus Q prime. So in the expression of efficiency, which is actually equal to T1 minus T2 by T1, which has been obtained from the TS diagram, we can equate this with the expression Q minus Q prime by Q. So it is T1 minus T2 by T1 equals to Q minus Q prime by Q, and from this we can conclude that Q minus Q by T equals to constant. That means the heat change by temperature, this ratio is a constant, and this is the mathematical form of the second law of thermodynamics. Now if the diagram would have been in the ST this way, then it would look like this. Okay, AB, this is isothermal reversible expansion, because during this change temperature remains the same. Okay, isothermal, so there should be no change horizontally, there should be a vertical uplifting. Okay, only the entropy is increasing due to expansion. Then this B to C, this path is due to drop of temperature due to adiabatic expansion. Okay, but temperature remains the entropy remains the same, because dq is constant, dq is 0 here. Okay, and then this rectangle CD to DA. So the path starts from here A to B and ends from here from D to A. So this is the point where the cycle was started. Okay, and if this diagram PV is drawn in the reversed way, that means V versus P, then it would look like this. Here, isothermal reversible expansion and adiabatic reversible expansion. One thing you must mark here, that the slope here for isothermal, the slope is greater, and for the adiabatic the slope is less steep. Why? Because during PV diagram, the value of tan theta has now been reciprocated. Okay, so for the adiabatic reversible expansion, tan theta was greater for adiabatic than isothermal, but here since they have been reciprocated, so the result would also be reversed. That means here the slope would be more steeper for isothermal expansion, and here would be less steeper. That is why the curve looks like this. So the journey starts from here A at this point, so this is marked in bold, and then showing this arrow that it goes to B, then B to C, C to D, and then D to A. Here the journey is over. Thus the cycle is completed. AB, BC, CD and DA. Okay, So this way the Carnot cycle would look is if V is plotted in the y-axis and P is plotted in the x-axis. So that's all for this lecture. Thank you. Have a nice day.